Previously, we looked at transducers, which tells us how we can produce and detect X-ray ultrasound waves, and these are longitudinal waves in a certain frequency range. So in this next part, we're going to look at what happens to the wave when it's traveling through a human body. Okay, it's come out of the transducer. What happens? One effect that we're going to look at first is reflection. So this will be the first video. The next video, next section of this subtopic will be on absorption, also known as attenuation. So these are the two effects of waves that we'll be looking at. Refraction and scattering, we're just like, sure, but we're not going to focus too much on that. So let's start off with looking at reflection. Let's start off by trying to remember a bit, what does it mean to have a reflected wave? So here, this diagram is a wave pulse down on this side, and it's on a string, like a rope, you know, you tie a string here, you tie a string here. But why is this string so thin on one side, but so thick on the other side? So this is what we call a boundary. Ooh. On one side, you have a very thin string. On the other side, you have a very thick string. So there is a change in medium. So this is a boundary where there is a change in medium. What does medium mean? Medium is where the wave travels in. So how does it look like? What happens when you send a pulse down the string? There, looks something like that, this GIF. So you have pulse come in. Ooh, why got two? Okay, let's calm down a moment. Pulse is traveling to the right. And once it goes to the black area, it continues on. So coming to the right, continues on in the black. But notice a few things. Number one, when the pulse comes in, it's a very large amplitude. Once it crosses the boundary, the amplitude becomes smaller. See the black color one here? You see the incoming one? And goes out. So this is what we call a transmitted wave through a different medium. The string is thicker. But notice another strange thing. Miss, what is this upside down small little lump? Oh ho ho. That is called the reflected wave. So there's a few things happening here. Number one, wave comes in, reflect, but also transmit. That is what we're going to learn about in ultrasound. So let's say you are having an ultrasound and you say, I want to scan some part of the body. So I will have what we call an incident wave coming in towards a certain medium. Okay, so I'm going to label this as our, let's call this incident wave, shining into incident wave, shining into a certain medium with a intensity of I. Let's just call this I. Sometimes you see them call it I naught. It's fine. It's I. You just know it's an incident wave. And down here is what we call a different medium. So I'm going to color this pink to show that it's something else, like, you know, a muscle or some other thing. So this is what we call this black line. It's what we call the boundary between media, different media. So maybe the section down here could be muscle. That's why it's pink color. Up there could be, I don't know, air, fat, something else. As long as it's some other material, some other media. Okay, so it's a boundary. What happens? So just now we saw one will be transmitted and then one wave will be reflected. So the same thing happens here. So I'm going to use a 2D drawing to kind of show what happens here. So firstly, you will have some kind of transmitted wave, which kind of looks, ooh, this is a little bit too thick. Something like this. Okay, so this one we're going to call it the transmitted wave. I'm going to call it, give it that name, transmit. What does transmit mean? Transmit means go into the medium, go into the muscle. So this is the transmitted wave. And we often say that it has some intensity of I for intensity. And we're going to use IT. If you're wondering, Miss, why this wave go at a funny angle? Oh, this is the effect called refraction. So there's some refraction happening here because you are going through medium of different density. So you see the wave supposed to go straight here, right? But then it bends down towards the middle line. You got to remember a bit of your SPM and IG or what you learned in secondary school. But don't worry, we're not going to worry too much about refraction in this chapter. We're just going to focus on reflection and absorption a little bit more. So, okay, one part of the wave will get transmitted. Another part will get reflected. So we are going to use, what color shall I use? Blue color. Sure, let's do blue color. So another part will get reflected out like this. And this is what you call the reflected wave. And this wave, we say it will have an intensity of, since reflected is R, I, R. Okay. So these are effects of waves, reflected, transmitted. Now, how do all these relate? Here's one thing to note. So how these intensities all relate is that the incoming incident intensity, I, or intensity I forgot to label that here on the left side. So intensity I is going to be the sum of the reflected intensity plus the transmitted intensity, all added up together. So you could think of it this way. If you send in 100% of the wave, and then maybe 20% got reflected, pew, how much is transmitted? 100 minus 20 is 80%. Okay, so that's just coming in, come in, how much reflected, how much actually go through. That is how you can think of how these three intensities are related. Okay, one last thing to know before we go through this is, when you're doing ultrasound scans, all this thing, we are going to, we draw these lines, but they're actually representing waves. So these are longitudinal waves, so usually we draw them like this, right? But we're tired of drawing all these waves all the time, bend here, one bend there. So we're just going to draw a straight line to represent the wave traveling in a certain direction. Also, one thing to note is, we are not going to send a continuous wave. Okay, this is called continuous. So it just keeps going on and on and on and on forever. We'll sometimes use this squiggly line to represent the wave. We are going to use pulses in ultrasound. Pulses or waves. So zip, 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 no pulse. Zip, 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 no pulse. Zip, 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 zip. So you have wave, no wave, wave, no wave, wave, no wave. And then we send them in the direction of these arrows. So some get reflected, some go in. Why we want to use pulses? We'll learn more about pulses later in this chapter. But the reason why we use pulses is because your crystal, you only have one transducer. Your transducer is going to emit out the wave, hit the boundary, whatever happened. Then if it reflect back, wow, then you're going to have so many waves all overlapping together. And you're going to have some problem there because your transducer crystal can only handle one at a time. It cannot emit and detect at the same time. So using continuous wave is not good. We're going to do them in pulses. Also, it helps that the reflected signal is distinguished from the emitted signal. So the transmitted one go in, reflect back. Oh, at least you can tell which one is which one. Okay, so you can see this one's going in. Then a few minutes later, something comes back. It's very clear cut. If not, you're going to have some big mess that looks like this, where you have some transmitted waves, some reflected waves, transmitted, reflected, and then got a standing wave. Oh my goodness, it's just too much. We're not going to think of continuous wave like this. So just know, we're going to do them in pulses, but not continuous strings of ultrasound wave coming in. And these are the reasons. I just screenshot this from a mark scheme. They will ask you why so just keep this in mind as we go along. You will talk about this more. So back to this transmission and reflection. Two things that you need to know. Wave is transmitted, but also a portion of it is reflected back to the transducer to detect. Now, how do we know how much is reflected? This percentage, I just simply create numbers. How do we know what the actual values are? Is there a way to calculate them? Yes, there is. And the beauty is, there is an equation for it. So when we think of things like air versus muscle, for example, these are two different mediums, air, muscle. We could think of density of air, density of muscle, to differentiate them, but something's not quite right, because if you say air has a certain density, the wave of the speed is different in air, different in muscle. So instead of saying just comparing the mediums by comparing their density, we create this new thing called acoustic impedance. Ooh, what is acoustic impedance? Well, we can say the acoustic impedance is the product of two things. Product of the medium's density. So in this up here diagram, air is a medium. Muscle is a medium. Bone is a medium. Water is a medium. So product of medium density and wave speed in the medium. So product, two things, medium density, wave speed. Now this is a better picture of how a wave travels through mediums. It's not just the medium density. How fast is the wave moving through the density? So for each material, we have its own specific acoustic impedance. There's a formula for this. I'm going to write it out for you. So we calculate the specific acoustic impedance Z we use Z or Z, however you pronounce this. This will be the medium density. What's the density of muscle, density of bone, times the wave speed. Now, this C is not the speed of light, so don't confuse this. It's just speed of wave. So I'm going to put a box there. It's a pretty important equation. And, oh yeah, might as well write some reminders. This is wave speed. This is the density of medium, so also known as the medium density. And this whole thing has a certain unit. I'm going to write that down too. The unit of acoustic impedance is commonly in SI base units kg m-2 s-1. They usually give it to you in the answer, but for you to know, this is how we can think of it. Alright? Now here's an example of different kinds of material and their specific acoustic impedance, also known as their Z value. You can take a look. Medium is a type, speed is C, and Z is this one. Okay, so let's see. Which one do you think has the highest impedance? Look very carefully. Very high impedance. Looks like the largest is bone. Ooh. Largest. And you can also see that the speed of this ultrasound in bone is also the highest. Bone is very dense and the wave travels through bone very fast, and that gives you a very large acoustic impedance because, you know, acoustic impedance is density times the speed. Which one you think has the lowest? Look there. Well, all these are 10 to the power of 6. The smallest would be air. So this one has the lowest or smallest acoustic impedance. So speed of, I guess you can say speed of sound in air, speed of ultrasound in air is also roughly in the same range. 330, very slow. Waves travel very slowly in air. Longitudinal waves, they are of this type, ultrasound. Very slow. It's like music, very slow. And acoustic impedance is so small. So small compared to everything else. So this is how we can compare different kinds of values. So the reason why we bother to create this new thing is so that we can use this Z or this Z to quantify the relative magnitude of reflected and transmitted ultrasound. Oh, you can use this Z to calculate how much is reflected, how much is actually transmitted. So there's another equation for that. Let's look at it. So when you have a wave incident normally on a boundary, say something like this on the right next to my head, let's scroll this down. There will be some reflected and some transmitted. So I'm going to do the same thing. I'm just going to color down there pink to show that it's a different kind of material here. We're going to say the first material up here has a specific acoustic impedance of Z1, down there Z2. So there will be some portion that is transmitted. What color did I use? Purple transmitted. Okay, let's use purple. Let's stick to that. So some amount will be transmitted. Some amount will be reflected. I'm just going to draw all vertical just to show. They're supposed to be all on top of each other, but just so it's easier to see, I'm going to separate them out. Anyway, this is IR. Okay, we can use this magical Z to find how much is reflected, a ratio. Okay, so this thing, there's an equation. They usually give it to us. We don't need to be able to derive it, but here's how it looks like. So we have this intensity reflection coefficient, alpha, and it is calculated by measuring the reflected intensity over the original. So take a look at the diagram. How much actually come back versus how much goes in. Can be a percentage, can be just a fraction ratio. And this equation usually is given to us in the past year, but it's good to also memorize it. This is Z2 minus Z1, the difference between how different are these two mediums squared over the sum of their acoustic impedance. Z2 plus Z1. See, up there is minus, down there is plus. That's just the difference. Okay, so this one, I'll put a box on it. It's kind of important as well. Usually given in past year, but once in a while they don't. Make sure you know what that is. So this will tell you how much is reflected. Maybe this is 30% of the original. Ooh. Okay, that's that number, 30% or 0.3, depends on how Z1 and Z2 compare to each other. How different are they? So let's look a little bit deeper into how to think of this ratio, this reflection ratio. Okay, let's see. So what is this ratio tells us is that how much is reflected, okay, when you have an incident ray. So I can write it in this way. If Z1 and Z2 are very similar, means they are almost the same similar medium. Could be bone and bone, or muscle and a slightly different muscle. Similar acoustic impedance. Maybe they are same medium. Okay lah, just similar. Or exactly the same. What happens to this whole reflection coefficient? If Z1 is the same as Z2, same minus same, this whole thing becomes almost zero. The difference is very small. Okay, if these are similar, difference is small. So this whole thing becomes almost zero. So your coefficient, reflection coefficient, A will roughly be almost zero. Very, very small. And what does that tell you? That means there is there is little to no reflection of this wave at the boundary. So you can kind of tell what material it is. If it's not reflecting, it's like kind of same acoustic impedance. And just now we have that whole chart that tells you what material it is, right? Another scenario possibly is, what if Z1 and Z2 are very different? One is air, one is bone. Like just now we saw the largest and the smallest. So in that case, if Z1 is very different from Z2, very different, then your alpha is going to be very large, almost 1. 1 is the largest number, okay? So that'll be 1. And what does that tell you in words? It means there is a lot of reflected intensity when you go to the boundary. Large reflected intensity. I should say large reflected. Change the sentence a bit, sorry. My head is blocking. There we go. There is a large reflected intensity. Okay, so let's know the difference between how to understand the usage of this equation. Number 1, know that if both material have very similar acoustic impedance, like these two, 1 material, 2 material, then there will be little to no reflection. And that is, your alpha will be very, very small, almost 0. But if there are very different acoustic impedance of these two medium, and then you send a wave in, then a lot of the wave will just bounce back. Okay, so that will be alpha equals to 1. There is a large reflected intensity. If you ever feel strange of how to think of this bone and muscle, you think of this, okay? There's a wall, and you shout into the wall, you send some wave. Most of it should bounce back, right? But actually, there's a small amount of wave that go through. You don't believe me? You go to your room, you shout at the wall. Ask somebody on the other side of the wall to listen. They can hear very soft, but most of it will bounce back at you. The reason is because one side is air, the other side on the wall is concrete. Very large acoustic impedance. Very different, so large reflected. Most of the wave will bounce back. Only a bit would go through. So you apply this same thing. We are going to do this a lot in the next few past examples. We'll do things like muscle, bone, fat, air, and all kinds of different combination of materials. But before I end the video, one last tip about this equation. I know it looks very weird, very strange, but in sentence, when you see this, it means fraction of intensity. Okay, this is preparing you for the partial that we'll look at soon. Fraction of intensity reflected at boundary. How much is reflected? That's your alpha. That's the coefficient. Reflected at boundary. And this equation can only apply at boundaries. Only boundary. You are looking at what happens at a boundary. How much is reflected? Okay, so we're looking at a fraction of intensity reflected. Only at boundary. This first part is just reflections. Alright, so that is all for this intro on how to think of reflections. And the reflection, the amount reflected, depends on how different these two mediums are. One is air, one is something else. they have their own specific acoustic impedance that depends on their density and also wave speed. It's like density lah, but multiplied by wave speed, because wave speed is different. And that is the whole idea of reflection of ultrasound. So that's all for this video. I'll see you in the example. We'll try out together how to better understand this in context of ultrasound and medical imaging. See you in the next one. Bye bye.